All right, guys, so this is our first Flip the Classroom lesson of the second semester. In this lesson, we will be talking about simplifying trig expressions and proving the equivalence statements for trig expressions. Right? We're going to break this up into probably 3 videos, and this is going to be the first of those videos in which we're going to start talking about trig expressions in general. So what do we mean when we talk about trig expressions? Well, with trig expressions, basically we're looking at expressions that are multiplying, dividing, adding, or subtracting trig functions. We've got an example of a trig expression right here. Here we're only multiplying and dividing, but we could be adding and subtracting as well. In general, we want to take note of a difference in notation with regards to powers. In our numerator right here, we've got sine squared x, and really what that's saying is the ratio of sine of x squared, right? Whenever we are raising a trig function to a power, we always apply that power directly to the trig function itself, right? And this avoids any confusion with potentially having the rotation inside the trig function being raised to that power. So right here, in general, when we're simplifying trig functions, we're going to be saying that we are evaluating these trig functions for a unique angle. In this case, that angle is x. And basically what this means is that we're going to be getting numbers, right, for these ratios that we'll be able to cancel out. In other words, right here, the sine x we're squaring in the numerator, right, is going to be the same number as the sine x we're seeing right here in the denominator of our expression, right? Now, because these ratios are representing unique numbers that we'll be able to cancel out, we're really going to be able to simplify these expressions in the exact same way we would simplify an algebraic expression involving just variables. Here we have an algebraic expression involving just variables that is algebraically identical to our trig expression, where sine is represented by y and cosine is represented by x, right? If I were looking at this algebraic expression involving just variables, I might start by simplifying the denominator. Right here I can see I am multiplying x times y over x squared. Right here I'm going to be able to cancel out the x I'm multiplying with one of the two x's I'm multiplying in the denominator of my denominator, and that will give me y squared over y divided by x. And now right here I'm dividing by a fraction, which is the same thing as multiplying by the reciprocal. So right here I can say I've got y squared times x over y. And similarly, again, we can cancel one of the y's we're multiplying in the numerator by the y we're dividing here, and we will get this expression as equal to y times x. Now, basically, when we simplify our trig expression over here, we're going to see all of the same algebraic moves. Right here, I'm multiplying cosine, and I've got cosine squared in the denominator, so I'm going to be able to cancel out one of the cosines in the denominator of my denominator. Then I've got sine squared x over sine x cosine x. And now right here, I can say that I've got sine squared x times the reciprocal, cosine x over sine x. And now we can cancel out sine x's, and we're going to be able to say that this statement is equivalent to sine x times cosine x. Now right here we can see that this expression would be a lot easier to evaluate for an angle x than our original expression right here, right? So we can see the value of simplifying trig expressions pretty much right away. Now, in general, we're not always going to be evaluating or simplifying trig expressions that are so readily easy to simplify. If we were looking at something like secant theta over cosecant theta times tan theta, we would have to say that we couldn't immediately cancel out any trig functions in the way that we did with our first expression right here. But what we're going to be able to do is use what we call trig identities to make substitutions where we'll be able to represent an expression like this with some of the same trig functions, and then we'll be able to cancel out just like we did right here. So let's go ahead and start defining those identities. So what is a trig identity? Well, a trig identity is basically a way we can represent one trig function with other trig functions, or just another trig function in general. All right, so right here, we'll start by defining our basic identities, which are made up by our reciprocal identities and our quotient identities. In general, we can start defining our reciprocal identities right away just by looking at trig functions as we define them on the unit circle. So right here, we can say that cosecant of an angle theta is going to be 1 over y. Well, we know that on the unit circle, sine of theta equals y. So right here we can say cosecant is actually 1 over sine theta, or could be defined as 1 over sine theta. If we solved for sine with this expression right here, we would get 1 over cosecant theta, right? Similarly, right here we can see that secant on the unit circle for an angle theta is 1 over x. We know that cosine is x, so we'd be able to define secant as 1 over cosine of theta. And right here, if we were to solve for cosine, we would get cosine as 1 over secant. Really what we're seeing here is that we can define trig functions as 1 over their reciprocal, and we can extend this to tan and cotan. Tan is going to be 1 over cotan of theta, and right here, cotan is 1 over tan of theta. And in general, we've already done this when we've evaluated trig functions in the calculator. Right here, if we want to evaluate cosecant of an angle, we would generally type in 1 over sine of that angle, and we'd be able to see that number on the calculator. So we've already seen this before. We're just sort of defining it in terms of these reciprocal identities that we're going to be able to use in our simplification of trig expressions. So right here, the quotient identities are actually pretty easy to come by. We know that tan is y over x, right? So right here, that's going to mean that we can say that tan of theta is equal to sine of theta over cosine of theta. And cotan we know is x over y. And right here, we're going to be able to say then that cotan of theta would be equal to cosine of theta over sine of theta. And one thing we might want to take note of right away is that every trig function can be defined by sine and cosine in some way. We've got the quotient identities for tan and cotan. We've got cosecant as 1 over sine, and secant as 1 over cosine. And of course, sine and cosine are themselves sine and cosine. So in general, one thing that we can take note of is just with our basic trig identities, we could define every trig function with sine and cosine in some way. Okay, so let's look at the Pythagorean identities. The Pythagorean identities come from us looking at looking at reference triangles on the unit circle. So right here, let's say I've got a reference triangle on the unit circle that comes from some rotation theta. Well, right here, I know that the opposite side is going to be y. I know the adjacent side is going to be some x, right? For some ordered pair, we have as x, y on the perimeter of the unit circle. And I can say that the hypotenuse of this reference triangle is going to be r, which we know to be of length 1, right? So let's take this reference triangle and bring it down and take a look at it. Now, if I were to apply the Pythagorean theorem, I could say here that for my reference triangle, which is a right triangle, I have x squared plus y squared equals r squared. Well, right here we know on the unit circle that the x values are cosine of theta. So right here we could substitute in for x cosine and get cosine squared theta. And we know that the y values are sine of theta. So right here we could substitute in sine of theta and get sine squared theta. Similarly, right here we know, since this is a reference triangle within our unit circle, that r is 1. So right here we've got cosine squared theta plus sine squared theta equals 1. And that's our first Pythagorean identity. Right here we get the other two Pythagorean identities by dividing by sine and cosine. Right here, if I take this expression and divide both sides by cosine squared rather, if I divide both sides by cosine squared, I can distribute the division of cosine squared to both terms on the left side and get cosine squared theta over cosine squared theta, and sine squared theta over cosine squared theta. And right here, cosine squared over cosine squared is going to be 1. We have sine squared over cosine squared, which will give us tan squared theta, and 1 over cosine squared theta, which with our basic identities we can identify as secant squared theta. So that's our second Pythagorean identity. Now right here, if we go through and divide everything by sine squared theta, in the same way we divided everything by cosine squared theta, we can distribute that division of sine squared theta to both of the terms on the left again. And right here, we'll be able to see cosine squared theta over sine squared theta as cotan. Sine squared theta over sine squared theta is 1, and 1 over sine squared theta is cosecant squared theta. And there is our third Pythagorean identity. So there are the Pythagorean identities and the basic identities. Now right here we can talk about even and odd identities, and basically this comes from the fact that every trig function is either even or odd, right? And we can see that from the graphs of our trig functions. Right here, if we were symmetric with respect to the origin, basically being reflected diagonally across the origin, we would say we are odd. And if we are symmetric with respect to the y-axis, we would say we are even. So right here, immediately, we can say that sine is odd, cosecant is odd, tan is odd, and cotan is also odd. Since all of these trig functions are odd, we know that by the definition of odd functions, which tells us that if a function is odd, when we plug in a negative x, it's the same as making the function negative. That right here, when we plug in a negative rotation, it's the same as making that trig function negative, right? So immediately we can say that sine of negative x is equal to negative sine of x, and that follows for all the other odd trig functions. Right here, we can see that cosine and secant are even trig functions. They're both symmetric with respect to the y-axis. So right here, by the definition of an even function, we know that when we plug in a negative x into an even function, so f of negative x, we get the function back. It's the same as plugging in a positive x. So right here, we know that cosine of negative x equals cosine of x, and secant of negative x would equal secant of x. Right? So that's basically a way for us to deal with negative rotations inside our trig functions. So moving on, we can move on to our co-function identities. Now right here, we've got a reference triangle with an angle of perspective A. So there's the angle perspective A in our reference triangle. Now, right here, we can go through and define our trig functions for that reference triangle. But what if we were to change the angle perspective from our angle A to our angle B? When we look at our triangle from angle A, we can say that the y value is the opposite, or the y length is the opposite length, and that the x is the adjacent. And we know r is always going to be the hypotenuse because it's opposite the right angle. But what if we were to take B as our angle perspective? Well, then the y would change from opposite to adjacent, and the x would change from adjacent to opposite. So right here, we can say that sine of A equals y over r, but cosine of B also equals y over r. Similarly, right here, if we look at cosine of A, that's x over r, but right here, that's also sine of B. And if we go down, we can sort of see this relationship with all of our co-trig functions. So right here, tan of A is y over x, but if I switch these two guys, that would be basically looking at the reference triangle from that angle B. We switch opposite and adjacent, and that gives us cotan of B. Right? So switching the angle perspective is really switching our definitions of opposite and adjacent, and what we're getting is the cotrig functions from that other angle perspective. So secant of A is cosecant of B. And right here we can say cotan of A is x over y, but right here tan of B would also be x over y, and cosecant of A is r over y, but right here we could say that secant of b would also be r over y. So the relationship we're seeing with trig functions and their cotrig functions is that the cotrig functions are basically the same ratios from that other angle of perspective, right? So if we can define that other angle of perspective, really we've got an identity here. We can say that we know that since this is a right triangle, that C is 90 degrees, right? And that means since a triangle has 180 degrees, that A plus B must also equal 90 degrees. Now, if we define B as that other angle, we could say that B would be 90 degrees minus A, right? So the other angle is always going to be 90 degrees, or a right angle minus A. Now, in general, we're not going to be defining our angles in degrees here. We're going to be defining them in radians. So right here, for an angle theta of perspective, the other angle, and I'm going to use that little symbol for the other angle, is always going to be equal to pi over 2, which is a right angle in radians, that's equal to 90 degrees, minus theta, right? And right here we've got these identities laid out for us. So right here, if we look at these identities now, see if I can pull that down, we've got sine of theta as equal to cosine of the other angle. And that's how we want to think about our pi over 2 minus theta, right? So cosine of pi over 2 minus theta is the other angle in that reference triangle. Tan of theta is equal to cotan of the other acute angle, or the other possible angle of perspective. Secant of theta is cosecant of the other angle, and we see the same thing for the cotrig function. So cosine of theta is equal to sine of that other angle. And those are this is the co-function identities here. Okay, so let's go ahead and take a look at this page right here. This page is basically just all the identities compiled. When you print this out, this is a good tool for you to use when you're going through your problems. Let's take a look at simplification of trig expressions for a unique angle theta or x. So right here, our goal is to reduce the expression to the least possible number of multiplied trig functions in the numerator, not necessarily sine and cosine. We've got a couple strategies here. If we look at our first trig expression, we've got secant of theta over cosecant of theta tan of theta. And in general, if we see expression, if expression is multiplication and division, we can convert the terms of sine and cosine. So right here, changing everything to sine and cosine is going to give me my entire expression defined by either sine or cosine, right? Defined with basically sine or cosine. And if everything's in terms of multiplication and division, we're going to see things start to cancel out. So right here, that's a good strategy for us to try with A. We've got secant of theta over cosecant of theta times tan of theta. And right here, if I change everything to sine and cosine, I get secant as 1 over cosine of theta. And then that's over cosecant, which is 1 over sine of theta, times tan of theta, which is sine of theta over cosine of theta. Now right here, with these substitutions I've made, I can start making some cancelizations. Right here, we see a sign in the numerator and a sign in the denominator. So right here with our multiplication, we can cross-cancel these guys, right? And then we're looking at 1 over, let me change this to blue. So right here we're looking at 1 over cosine theta over 1 over cosine theta. And at this point right here, we can multiply by the reciprocal. We can also spot that we've got the same numerator and denominator. But if we were to multiply by the reciprocal, we would get 1 over cosine theta times cosine theta over 1. And right here, we would similarly see our cosines cancel. And basically what that's going to give us is this entire expression simplifying down to 1, right? So right here, whatever angle we plug in, right, we're going to see our expression simplify down to 1. So right here, I'm going to let you guys try B and C on your own, and we will come back and look at these guys in a second. Okay, so looking at these two guys, B, we've got cotan of negative x times tan of negative x. Right here, we know that both of these functions are odd, so that's going to give us negative cotan of x times negative tan of x. And right here, when we multiply two negative numbers, we get a positive, we'll just write this down here, cotan of x times tan of x. Now, at this point, I said, okay, well, right here, I can, since I'm seeing multiplication between these two trig functions, I know I can change everything to sine and cosine, and then I would see cosine of x over sine of x, sine of x over cosine of x, and again, I'll be able to cancel with the multiplication of my fractions and get down to just 1. Now, that's not the only way for us to do this, and I want to point that out right here. You could also spot that because cotan and tan are reciprocals, that we would be able to say that cotan is also 1 over tan x, and that right here we could say 1 over tan x times tan x also will give us 1 when the tan x is canceled. Right? So this is a strategy we can use, but it's not something we always have to use. Another thing you could say is because these two rotations are both negative anyway, we could really wait till the end to evaluate this. But in general, this is sort of something that I think we can take care of right away. Whenever we see a negative rotation inside our trig function, we're always going to be able to evaluate with the even-odd identities. Okay, so right here for C, we can immediately see that we've got pi over 2 minus theta, which is the other angle for our reference triangle. We might think about it as the co-angle, and that means that we can say that cosecant of pi over 2 minus theta is secant of theta, right? Now, at this point, I'm going to see if I can pull this down a little bit. We have everything in terms of multiplication, right? So we can change everything to sine and cosine and let things cancel out for us. Right here we've got 1 over cosine theta for our secant theta, and cosine squared theta, and tan as sine over cosine. Now right here we're seeing one of our two cosines that we're multiplying cancel out with the cosine in the denominator of our first multiple, and then right here the second cosine is going to cancel with the cosine of the denominator of our sine over cosine, and that gives us just sine of theta in the end. Okay, so right here with our next problem, we are seeing secant squared theta minus 1 over cotan theta. So just changing everything to sine and cosine isn't necessarily going to help us here. What I want to recognize is if I'm seeing an addition or subtraction within my trig expression, I want to try to get to a Pythagorean identity. So right here, if I see addition or subtraction, try to use a Pythagorean identity to sub one term for two terms. So basically, let's see, really the reverse of this. We want to substitute two terms for one term. And basically what that's going to do is get us closer to an expression that is just multiplication and division, which is going to be a lot easier to simplify. Now right here, none of my Pythagorean identities have a subtraction in them, but what I can say is that if I go back to the Pythagorean identity that involves secant, I have 1 plus tan squared theta equals secant squared theta. And if I manipulate this identity, right, by subtracting 1 from both sides, I'm going to get, right here, tan squared theta equals secant squared theta minus 1. And then I'll be able to use that identity. So I'm going to get rid of this guy because he's not really helping me. But the manipulation of that identity helps me. Oh, this is going to be a little bit of a mess. Let's see if we can get rid of that. The manipulation of that identity helps me substitute one term for two terms. And that's what we're trying to do here. We want to see if we can substitute one term for two terms, which will allow us to get closer to an expression that is just multiplication and division. So right here I'm going to say I'm going to be able to substitute in tan squared theta here. So we've got tan squared theta over cotan of theta. And then right here I can change everything to sine and cosine. The other thing I could do is I could know that cotan is actually 1 over tangent. So I could get this entire expression in terms of one trig function, tangent, which is actually a little bit of a shortcut. And right here we can say that tan squared theta over 1 over tan theta is equivalent to our expression right there. Now I'm dividing by a fraction, which is the same as multiplying by the reciprocal. So we can say that tan squared theta times tan of theta is equivalent to our last step right there. And then finally, right here, how many tans am I multiplying? I'm multiplying 3, so that's tan cubed theta. And that would be the simplified expression. Okay, so why don't you guys go ahead and give this next one a shot on your own, and we will come back and look at it together in a second. Okay, so we're seeing an addition between two terms, so we know we're going to want to use some Pythagorean identity to substitute one term for two terms. But immediately right here we've got a problem because we've got secant theta, tan squared theta, and our first term is secant theta. Now right here, one thing I can do is I can recognize that I'm multiplying secant theta in both of these terms, and if I factor off secant theta, I actually get that second Pythagorean identity of 1 plus tan squared theta equals secant squared theta, which will be a big help to me, right? So right here, factoring off that secant theta from both of our terms right there gives me secant theta times 1 plus tan squared theta, and then I can substitute in for 1 plus tan squared theta, secant squared theta, and now I've got secant times secant squared theta, and that gives us secant cubed theta. Now, if you're having trouble seeing that, another thing that you could do would be to change everything to sine and cosine. And I know that a strategy we talked about for mostly multiplication and division, but it's also a good strategy when you're not sure what to do. So right here, if I did that, I might have something that looked like 1 over cosine theta plus 1 over cosine theta, and then right here times, we've got sine squared theta over cosine squared theta. Now at this point right here, I could say that I have 1 over cosine theta plus sine squared theta over cosine cubed theta, right? And now at this point, if I multiply by cosine squared over cosine squared, I can get common denominators. And that would give me cosine squared plus sine squared, cosine squared theta plus sine squared theta. Can't forget the angle. It's not a number without an angle. And that'll be over cosine cubed theta. Now right here, this is our first Pythagorean identity in the numerator, which would give us 1 over cosine cubed theta. And that right there is secant cubed, theta. All right, so some different ways to look at some of these. We're going to do one more video at least, and then we may hold off on that last video. We'll see how short we can get these. And we'll do a worksheet on Wednesday. All right, guys. See you Wednesday.